Hello everyone. Welcome to today's edition of the LSST Transient Variable Stars Science Collaboration Talk. Today we have Dr. Mahtab Gholami, who is currently a postdoctoral researcher at ENAF Capodimonte. Primarily she's working on photometry detection and classification of variable stars. From what I understand, she's currently working on the Galactic Bulge, but she has also in the past worked on local group galaxies, star formation histories, chemical evolution of stars. She has a varied and diverse background. So yeah, so without any further ado, I will give the stage to Mahtab. So yeah, Mahtab, floor is all yours.
Thank you so much, first of all, for joining and for invitation. It means a lot for me, and also I'm really sorry in advance for switching off the camera because my environment is not professional, so it's better to start to switch off. So I want to talk about our project that is gonna to be done in INAF in Capodimonte, Naples. The PI of the project is Massimo D'Allora. We are working on multi-band ugriz characterization of high-quality variable stars in Galactic Bulge and then bridging the gap to Rubin LSST. The goal of this project is 3D mapping of reddening, distance, and metallicity in Galactic Bulge using RR Lyrae stars and also providing the list of variable stars with a high quality that I will explain about that. To do that, we use the archived DECam data in all the bands UGRIZ, and also we are trying to add also the Y band to our photometric catalog to cover more spatial distribution. So we did individual PSF photometry on PlayID, that is enough high performance computer facility. Up to now, 6 proposals to use PlayID is accepted, and recently the 7th one also is accepted to use. And we did the calibration for our photometric catalog using Gaia synthetic photometry. And then we started to analyze the data and look for variables using generalized Lomskargel. Okay, at the beginning, I should say that at the present time, we know that Rubin LSST pipeline is not able to analyze the stars in very crowded fields. For example, in these 2 images, you will see the 47 Tucane and Fornax by DP1 catalog. In the crowded field, in the center of these 2 targets, you see that the stars are not resolved and the pipeline was not successful to analyze the stars in this area. And then for the area with the densities higher than these targets is completely unsuccessful. For example, consider bulge, that the density is huge. And if we want to use the pipeline of LSST, it would be very challenging for us. Here you can see the 47 Tucane by DP1 in the gray points, and in the center of that the DP1 couldn't resolve the star, you will see the colored parts that our photometry pipeline could be able to analyze the stars in the crowded field. So our photometric pipeline can be a benchmark for DPX for Rubin LSST. The area that we started to study in Galactic Bulge started by Saha field from B1 to B6. Then we extended the photometry process up to B14, and these days B14 is finished and we started for B15. We started the variability search by B2 field. And you know that we are using all the DECam filters, and in the R band for this field, we have 110 epochs. And this is the baseline of measurements for detecting the variable stars. Here, first I should explain that we have finally 14 million selected points in the B2 field and generally 9 billion total individual measurements in all the bands. So we provided the photometric catalog, and then we think about that, okay, we need to test our photometric pipeline by the overlapping area between each 2 CCDs. That DECam data contains 61 CCDs, and between each 2 CCDs is very important to check the photometric calibration. Here at the top, you will see the magnitude difference in the R band versus R band. And here, for those two bottoms, the magnitude difference versus RA and also versus DEC, that you can see that these sources between the overlap area for each two CCDs are very good calibrated and can be reliable. This is the initial color magnitude diagram of the B2 field sources in R band versus G minus R. And then we made a comparison with the B1 field that has been done in 2019. And our photometry catalog shows that it can be deeper in photometry around 2 magnitudes. That is a good opportunity for us to detect also the fainter variable stars. Here, you will see the spatial distribution of the B2 field in gray points, and also you will see the black points that are overplotted here. They are the variable stars that we finalize in the B2 field. And also it's very interesting if you see that there is a patches, for example, here, black patches here, also here, also here. The first patches that I'm showing you, is the globular cluster 6569 that is located exactly in CCD45, and Massimo D'Alloro is working on that. And in this area also you will see two globular clusters that are under analysis by other colleagues, and most probably there are some globular clusters that we didn't discover yet. And this is the final color magnitude diagram with the calibrated magnitudes in the R band and G band. Here you will see the finalized variable candidates in B2 field. Those ones that are common with OGLE catalog are shown with the black points, and others that are shown with the blue points are not common with OGLE. They are the new discoveries of us by our algorithm in the B2 field. But I should tell that some of them, the bright ones, are in common with Gaia DRT, but very few of them. Especially for the fainter ones, they are detected as a new discovery. Okay, how we detect the variables here? First, we put the threshold for the number of measurements and variability index. That is one of the outputs of our photometric pipeline. And then we started to calculate the period using the generalized Gholami algorithm. You will see the violet points here that are the initial sample after these initial selection thresholds. Then we want to find the best candidate of variability. So we don't want to find all the variables in the B2 field. We want to just find the variables with the high quality in the light curve. So to do that, we did a cross match between our catalog and also OGLE catalog, and we found the common sources, and then visually we checked all the light curves of sources in common with OGLE one by one in the R band. And then we selected the best and high quality variables in the light curves. You will see here the peach circles, they are the best OGLE candidates in our photometric catalog. Then we selected the area B based on this kind of selection, based on OGLE concentration. And we start to analyze this data here in this area. And I should say that this plot is power peak versus the power signal to noise ratio. The power signal to noise ratio, we mean the ratio of power peak to root mean square for each source. They are the outputs, the power peak is the output of generalized Gholami as a Fourier transform. And now I'm talking all the time and also afterward about the high quality light curve. What do I mean? If you see these two light curves at the top, you will see that they show clear periodic variability with at least 15 photometric measurements and full phase coverage. While in the bottom, you will see the light curve that it shows visible variability, but completely failure to meet the requirements for phase coverage And also we remove these kind of sources. However, they show variability, but we remove them from our catalog because just we need the best and in high quality light curves. These are some examples of variable candidates in B2 feed that are fitted. And this is one of the interesting example. They are managed in the R band. This is the variable candidate that you see the R band light curve. The amplitude of this variable is 0.06 magnitude in the R band, and it shows that our photometric pipeline is able to detect the variables with a very short amplitude too. Okay, at the end, after visually checking 61 CCDs one by one by eyes, and now you know I'm completely blind, I can't see anything, and checking everything to be in high quality and removing the not phase coverage light curve, we need to obtain the mean magnitude and also the amplitude of each variable. We use the ransack code that is a kind of Monte Carlo simulation. One of the important output of this model, mathematical model, is R2 parameter. This is the equation that R2 is calculated by. Yi here is the observed magnitude, and also this parameter here is the model, because in this model, you know that in ransack mathematic model, it starts to feed up to 100 lines in each light curve, polynomial lines, and then start to average among them and find the best fit for each light curve. Generally, if it shows that if the scatter of the model is bigger than the real data, R2 parameter become negative, and it shows that it's completely unsuccessful. So also, we added some facilities to ransack modeling, again, to check for us if the variable is in high quality or not. We call them flag 1 and flag 2. What do I mean by flag 1? Flag 1 means the light curve that after fitting, you will find that a star that in the phase light curve have at least 2 empty bins. Those ones that we removed from the catalog. And flag 2 are the opposite one. They have at most 1 empty bin. So we accepted them as the best and in high quality light curve. Then, after finalizing the list of variables, we plotted the period histogram. You will see here the OGLE variables in green, but I should mention that this is the OGLE list for all the galactic bulge because we wanted to have the good comparison between our sources and what OGLE found. The blue solid line is the period histogram for our variable list. You can see that mostly the variable list that we found are covering the period of RR Lyrae stars, and also for the various small period sources is doing more successful rather than OGLE. Here in the middle, you will see the amplitude histogram. Here, these OGLE are shown with the green and also for us with the blue. And you will see the extra part of this histogram that shows that our pipeline is doing well for the short amplitude variable candidates. But I should tell you something more about this plot. We know that OGLE catalog is managed for I band and V band. Here, I just plotted the amplitude in the I band for OGLE, and for us is in the R band. I know that they are not compatible. It's not a good idea to put them in one plot, but this is just for comparison. And at this plot in right, you will see the histogram of the R band. Here, we transform the magnitude of the I band for sources in OGLE to the R band using the equations, and you will see the good coverage of the magnitude histogram for those catalog. Okay, now I want to have very brief comparison between the B2 variables by DECam and also the OGLE. All in all, we found 76% of OGLE that were common in the selected area that we considered for variability search. And around 24% of sources were completely new discovery in our catalog. In this part, we also added something else to our project. We're bridging OGLE-IV to the ugriz photometric system by providing the ugriz band and the amplitude for each of them to all the OGLE catalog. So if you search for OGLE catalog using our pipeline, you will see the catalog that contains not only IVI and V band, but also the DECam filters for each OGLE catalog that will help a lot for our other purpose to research about variables or other physical parameter searching in this field. Now, I want to inform you about something very interesting. We found something. I talked about the R2 parameter as one of the output of Randstock modeling. We started to plot the relation between normalized power signal to noise ratio that I mentioned is a ratio of power peak to root mean square versus R2 parameter. Then we start to study about the outliers. How? By putting the color code here versus the error of R2 parameter. We saw that they have very small errors. So we started to study about them. At the end, after many studies, we found that the outliers points here are the best variable candidates. This is not machine learning code. We don't use any machine learning, just R2 parameter by the Randstock code. You can see some examples of light curves here that they show the high quality light curve. So it can be done. If you want to detect variables in any field, you can easily manage with the Randstock as a fitting, polynomial fitting to each light curve, extract the R2 parameter, and then plot this relation, and then just select the outliers as the bunch of the best and high quality light curves. If you need the best variables for doing physics or anything else. Okay, then we started to do some simulation. In this figure in left, you will see the simulation for one of our variable candidates in the B2 field, that is RR-AB type, with the period of 0.8 days. One of our colleague, Marcella Di Crescenzo, did the simulation. She did the simulation for GRIZ bands for this RR-AB type for DP2 catalog. And then they estimated that if we want to see the fully phased light curve to obtain the period, the amplitude, and other required physical parameters, we need 10 years to obtain this fully phased light curve for this source. But already using the DECam data, we have it in our catalog. So we have the period, we have everything about that. So it might be a good pipeline. Our photometric pipeline could be very useful for Rubin LSST, for variability search, and other, especially about the crowded stellar fields. All in all, what we did, we processed 9 billion individual measurements from 14 million sources across 61 CCDs visually using PlayID. And then we identified around 8,000 variable candidates in ugriz band, and then also we filled the gap by OGLE-IV. So at the end, we used Randstock as the polynomial fitting model, and we extracted very important output as R2 parameter. And we found that, okay, we can detect the best variable candidates in any field using R2 parameter without any machine learning or anything else. And also, our pipeline stands as a primary Italian contribution to the Rubin LSST community. We also used the list of variables as the reference catalog for WST survey. One of our very close goal is 3D mapping of reddening, distance, and metallicity using RR Lyrae stars. So we will use the RR Lyrae stars in B2 field, which are the part of them are in common with OGLE and also included the new discoveries. At the end, we are trying to add Y-band to increase the spatial coverage. And about machine learning, we tried to use machine learning for classification, the variables, the new discoveries that we didn't know the classification of them. About the sources that were in common with OGLE, we knew the classification because OGLE did that very perfectly, very beautiful. So we started to do machine learning using random forest in multi-band photometry purpose, and we found the good classification for the new discoveries. And at the end, we did the cross match with Gaia DR3 for the new discoveries. And it was very interesting because we found, for example, some RR Lyrae stars in common with Gaia DR3. And it was a kind of quality assurance that our machine learning is doing well. And it classified the variables correctly. At the end, we want to extend the classification facilities and make it more precise in the future. Already 2 papers are very close to submission. One of them about the variables in the Galactic Bulge with the classification of them, and another one about the fully automatic pipeline to detect the best variables in any field. So thank you so much for your attention. I'm ready if you have any question, more than welcome.
That was an amazing talk. Thank you so much, Mahtab. Let's go to questions.